The first presentation is entitled "The Coupled Axial Transverse Vibration and Stability of Rod Under Axial Impacts," and there are three authors, Professor Belyaev, Morozov, and Tovsnik, and the presentation will be given by Professor Belyaev from St. Petersburg.
Okay, ladies and gentlemen, it's also my pleasure to give this presentation. Also, first time in the church, not in the Russian Orthodox Church, but in Western World Church, let's say. Yes, but no problem for me. Okay. We, three of us are from the Institute of the Russian Academy of Sciences, and nevertheless, this study was carried out in cooperation with the Austrian Center of Competence in Mechatronics in Linz, Austria. And let me start. I will begin with a classical problem, just to say a few words about the static buckling. And then I will come to the dynamic problem. First of all, the so-called semi-dynamic buckling or static dynamic buckling, and then I will suggest you a number of dynamic approaches. And actually, what I'm going to report is just a classical problem, and without just a theoretical problem, I would say, without any practical application. Okay. This problem, statical problem, is well known, I think, to everybody. In the framework of the linear analysis, we have such a boundary value problem, and the solution has such a form, and the amplitude can be any amplitude, and certainly a shortcoming of this approach, and nonlinear approach is much more realistic, let's say, just because at least we will have for each force, for each axial force, and we consider a simply supported beam, we will have the amplitude, and we have, so to say, the buckling shape. It's well known. Also well known is the problem of the pre-curved rod, and this W0 means an initial curvature, and we will have topologically another stable branches, but nevertheless everything is well known, and this is just it's well known actually. Okay, and what is probably less known is the attempt made in the late 40s by two members of the Russian Academy of Sciences, Lavrentiev and Tichlinsky, and they suggested the so-called static dynamic buckling of the pre-curved rod. The rod is pre-curved, and the idea is the force is suddenly applied, so to say, and we will keep this force, and this axial force is the same in all cross sections. So it's typical for statics, so to speak. We applied the static in axial direction, and then we study the dynamic motion of this rod or this beam in the transverse direction. So the static in axial direction and dynamics in transverse direction. And if we consider the vibration mode or buckling mode number M, and also the solution also as a deflection is also in the shape number M, then instead of the partial differential equation we will have the ordinary differential equation. And if we introduce this lambda, and if lambda is a real value, then we will have, so to say, two exponential function, and so to say, this function describes the unbounded solution. And let me repeat once again, there is a number of buckling shapes or vibrations, number 1, number 2, number 3, and so on. And among all these eigenvalues, there is one which is maximum, the maximum eigenvalue. And this maximum eigenvalue describes, so to say, the solution which increase with a maximal instability rate. And you see, there is m, if we calculate this derivative, so to say, and determine this, the maximum of this lambda, then we will obtain the result that m and n don't coincide. It means if we applied the critical force, the Euler critical force number n, then not the n buckling shape will have the maximum rate, but another buckling shape, number m. Okay. For example, and there is some factor between, and namely square root of 2. So if we apply the third critical force, then surprisingly, the maximum instability rate will have the second instability shape. And if we will apply the force, then we will have, so to say, the maximum instability rate. We will have not the fourth buckling shape, but the third one. And this is a paradox. And you certainly know paradox is a Greek, an old Greek word which means some statement which contradicts itself. It might be wrong, it might be true, but anyway, we need, so to say, some additional studies just to be sure that it should be. Anyway, it needs an explanation. Okay, so the first step is quite reasonable, just to consider the dynamics not only in transverse direction, but also in axial direction. So everybody understands that the wave will propagate in axial direction, yes, but we applied, so to say, the Kelvin-Voigt trilogical model just to take into account the damping. And this axial force, it depends not only on position, but also on time. And we will use not the approach of the wave propagation, but we can expand the solution in terms of the axial vibration mode because of the dual possibility. And it's a very simple problem, like easily solve it and obtain the axial force, which of course will depend on time. It will be a number of harmonic motion, and then we will substitute. We look the solution for in terms of the bending mode, also instability shape, and we will obtain the generalized equation for ordinary differential equation for the generalized coordinates, and this part, for example, the very fact that here we can see the generalized coordinates for the axial vibration leads to the fact that we will have the ordinary differential equation, and here you can see the term which is time dependent. Yes, and namely the periodic or harmonic motion. So it's a kind of Messier equation, and if we just consider just the main instability region, because there is a mixture of all these parameters, and all these coefficients are presented here. There is, for example, in this eigen frequencies, there is a part from bending, and also this part of the axial force, and so on. And it can be easily solved, and we will obtain the instability region. But you see, The result is disappointing, I would say. For example, we can see here that the first longitudinal mode excites just the instability region number 12 on the bending instability, which is certainly not realistic. With this in view, we make the next step, and we will consider the general analysis, and we assume that this axial force acts just has a finite time duration, and the solution. Of course, I will skip all these calculations. But anyway, the final result you can see here. The solution looks like this. This alpha m is actually describes, as you see, corresponds to the buckling shape number m, okay, and this is responsible for the instability. And of course, a number of this exponential function are excited. Number 1, number 2, number 3, number 4. And for example, if we take the fourth Euler force, Euler load, critical load, so you can see that we will have such a line, I would say, and generally speaking, the first, the second, the one, and even the fourth will be excited. But the shape number 3 has a maximum instability rate because it corresponds to the maximum value of this alpha. And of course, it's a paradoxical situation probably. But you see, if we move slightly to the right, then we will deal with the number 4. And if we move to the left, then the second will be prevailing, let's say, in such a way. So it's the next calculation. Let me also skip this calculation. And if we obtain the complete picture, what I mean complete, I mean that it will be some curves which correspond to the exponential instability and also some parametric instability. So you will see that the amplitude growth or instability rate, whatever you like, at the Euler bifurcation is always greater than growth at the parametric resonance because they are lower in this picture. So parametric resonance is probably not so dangerous. However, if we consider only parametric resonance, if we consider also the combination resonance, you will have a plenty of opportunities just to show you how difficult is this problem because the number of parameters comes in play. Okay, now let me come to the nonlinear problem. If we consider the Euler elastica in the nonlinear statement, geometrically nonlinear statement, okay, and axial strain is considered, but statically. I mean, the inertia is considered only in the square in the transverse direction, but not in the axial direction. And here you see the result of the calculation. This small p means it's actually is proportional to the axial force. Okay, and P is equal to 1 corresponds to the first Euler critical force. And we consider the case in which P is a little bit greater than the first. So you see this end of the beam moves, and first of all we have, so to say, the first the first buckling shape, which increases, and slowly we will come to really, so to say, we consider very flexible rod. Yeah? But anyway, only the calculation demonstrate, but actually only the first buckling mode is presented here. However, if we take P is equal to 10, and what does it mean 10? P is equal to 9 means the third instability, the third critical load. It's a little bit greater than the third instability. Then 3 buckling shape will be presented here. And typical is also, yes, just yes, a note here appears, yes. And all these 3 shapes are presented, but the second one is prevailing. And in the case of the 20, it corresponds to the fourth instability, fourth critical weight. Now we will have, so to say, the presenting. So, of course, all these are presented, but the calculation demonstrates. Okay, and I have no time to explain the energy exchange. It's just calculated, but I cannot draw any conclusion from these pictures. And just a few words about the determination of the contact force, because such so to say a rectangular load is hardly possible to realize, not feasible, and more realistic is just to use some impactor. And we can calculate it in semi-analytical way by means of the displacement due to wave motion plus some local deformation by means of the Hertz law. But finally, we will have nonlinear integral equation and calculate this force. And we can also do it numerically. And just to compare these results, they're very close for the rectangular and cross-section, and surprisingly, they differ considerably for the circular cross-section. But anyway, we can calculate it, and we are going to do the same study, but for this loading force. Okay, and actually that's what I'm going to report. And just I would like to say that the problem demonstrates a very rich dynamics, which should be studied carefully. Okay, thank you very much for your attention.
The paper is open for discussion. Professor Naife.
Did not include the nonlinear terms from the stretching.
Yes.
There. And the other question is the inertia, axial inertia.
Is ignored.
Unless the mode number is small in the transverse, the axial inertia cannot be neglected. Third, fourth mode from the transverse deflection. You have to include the inertia in the axial direction.
Yes, we've done it. We've done it, so to say, for example, in this picture, but we cannot easily interpret it. So it's a problem, yeah, and we can do yes, but there's always too much information. And
some more questions. Did you observe some chaotic behavior in the response?
Not yet, let's say, yes. We just take this very, very classical problem and would like to study from each side, yes, and not yet.
Okay, no more questions. Okay. Thank you very much.
Okay, thank you very much.